10.4, number 26. There's a lot going on in this problem. It says baseball's hit with when it's 2.5 feet above the ground, leaves the bat with an initial velocity of 145 feet per second and a launch angle of 23 degrees. At the instant the ball is hit, an instantaneous gust of wind blows against the ball, adding the component of negative 14 feet per second to the ball's initial velocity. A 15-foot fence is 300 feet from home plate in the direction of the flight. So part A, find vector and parametric forms for the path of the baseball. Alright, so we can start. We've got X, we have horizontal and we have vertical components. So our X, or horizontal, is equal to X sub 0 plus V sub 0 cosine alpha t. So that's the general one. So our X in parametric form, we are not moved left or right at all, so our X sub 0 is 0. Our initial speed is 145, cosine of 23 t, and then we've got our wind gust going, it doesn't say the direction, but it is negative 14 so it's minus 14 t. So our X is 145 cosine 23 t minus 14 t. Okay, so that's our X part of the parametric equation. Our Y is generally equal to Y sub 0 plus V sub 0 sine alpha t minus g over 2t squared. We do have an initial Y, it's 2.5 feet, so Y equals 2.5 plus 145 is our initial velocity, sine of 23 degrees t minus, we're in feet per second, so 32 over 2t squared. Alright, so you can call that 16. So that's our X and Y in parametric form. If you wanted to write that in vector form, it would just be, you could write in component or linear combination with i's and j's. Okay, so that I will call good with part A. B, how high does the baseball go and when does it reach maximum height? So we have a formula, how high and when. So we have a formula, our Y max is equal to our V sub 0 sine alpha squared over 2g, but that's for ideal projectile motion, so we'll be able to figure out this, but that'll all be when it's 2.5 feet off the ground. So that is actually helpful. So our Y max will get us the maximum here, and then we can just add 2.5 feet to it, and then we will know how high the baseball actually goes. So 145 sine of 23 squared over 2 times 32 gives us some number, and if I add 2.5 to it, our maximum height is 52.655 feet is our maximum height. I guess we want, it also said when does it get there, so that's our Y, and we have a Y equation, so you can plug that in for Y right there and then solve for T, which looks like it'll be a quadratic equation. So 52.655 equals 2.5 plus 145 sine of 23t minus 16t squared. So you move that over, make it 0. I would probably plug it in the quadratic formula. So A is negative 16, B is this, and C is 2.5 minus that. and it gives us 1.77 seconds. Alright, so another way we could have done it is we could have, how high is it? We could have found, using calculus, we could find the derivative of our y function. So find dy dt. Okay, so that's the vertical velocity, and find out when it's 0. So set it equal to 0 and solve, and you get time, and that'll be 1.77 seconds also. And a third way we could have done it is, rather than using the parametric form, we could just talk about vertical velocity. And you know, if you start with acceleration equals negative g, then the velocity is negative gt plus v sub 0, and our position is negative g over 2t squared plus v sub 0 t plus s sub 0. So then we could plug in a gravity, initial velocity, and so on, and you would end up getting the same answer, 1.77, just doing it a different way. So you find the position at 1.77, and then you would get the maximum height, which is 52.655. Alright, we are done with B. Part C. Find the range and flight time of the baseball, assuming the ball is not caught. Alright, so maybe I'll just stay with the parametric theme right here. So we want to find the range and the flight time of the baseball, assuming the ball is not caught. So our y, we want to know when our y is 0. So we would set this equal to 0, and that'll give you the time in which it's on the ground. So if you set that equal to 0, plug it into the quadratic formula, you should get about, well, 0.3419, well, 3.199. That's the time which we're looking for. So we want to know the range and when, that's not the right number, sorry. So I'm looking at an answer for part D. So the time is 3.58 in which that occurs, and then you can just plug that into the x equation. So x of 3.58, plug it into our x equation right here, and we get 428.26 feet. So that's how far the baseball travels. Most ballparks, for sure. That's a pretty good poke. Did we answer the question? Find the range and the flight time. So we got the flight time of 3.58 seconds and the range 428.26. D, when is the baseball 20 feet high? So what do we know? We know that y is 20. So we can plug 20 in for y right there. Well, right here. So make that 20, and then you can move it over and again solve that quadratic equation, and that's when we have two times which is 20 feet high. You've got time of 0.3419 and 3.19. Makes sense because it starts at 2.5 feet high. If 20 feet high is like right here, it's going to get 20 on the way up and then on the way back down. So 2 times it is 20 feet high. How far is the baseball from home plate at that height? So we know the time at that, so we just want to find x of 0.3419 and x of 3.199. Plug that into our x equations. Your x equations right there, so plug that in for time, and we get 2 answers. X of 0.349 is 40.85 feet, and at 3.199 it's, let's see, 382.21 feet. And the last question, has the batter hit a home run? Well, we know in part D, these are the times in which it is 20 feet high. So it's 20 feet high at 382 feet. Our original scenario was a 15-foot fence 300 feet away. So it's gone to 382 feet somewhere over here, and it's still 20 feet high at 382 feet. So it clearly was a home run because it cleared this 15-foot wall. We could also find out when it is 15 feet high, so we can put 15 in for Y and solve for T and see if it's beyond this 300-foot spot. Well, the phone's ringing, so I'm going to call that good.